My name is Dror Dani, and in the next 25 minutes, I invite you to join me on a journey exploring the power of powderless in metal additive manufacturing. Hanan Gottait, the founder and CEO of XJet, myself, and most of the XJet team are going together for many years. Our expertise is in the ability to create ink and jetting it with industrial inkjet head in the right way. When I say the right way, it means that we can put over 220 million droplets per second with our newly introduced Carmel additive manufacturing systems. Our journey goes back 30 years. It started back in the early 90s with the creation of two-dimension wide format inkjet. It moved later to 3D polymer prototyping with the creation of Objet and the creation of PolyJet technology. Now, in additive manufacturing, with the introduction of nanoparticle jetting technology and the launch later this month of the Carmel product line here in the US, using this technology to create ceramic or metal additive manufacturing parts. We were very lucky to have investment of over $100 million over the years from world-leading companies. This allowed us to put together a team of more than 100 brilliant, outstanding, innovative people, and growing, mainly in our R&D labs, bringing an overall of way over 1,000 years of additive manufacturing experience and many thousands of patents by different employees. And they gave birth to more than 80 XJet basic patents and gave birth to this technology. Nanoparticle jetting. Nanoparticle jetting describes in a very concise way what we really do. It starts with creation of a special liquid where nanoparticles of either ceramics or metal are dispersed or suspended in a special liquid, which you may call ink. Nanoparticle jetting is producing or jetting layers of droplets. These droplets contain the nanoparticles, ceramic or metal, over the system build tray. We keep very high temperature, and this causes the jacket around the particles to evaporate instantaneously and to build a layer. Once we have a layer, we can put another layer, and so on and so forth until the part is ready. This allows us to build this drill that you see in the picture. Now, I don't know about the people at the back in the less expensive seats, but if you get closer, and Katie, maybe you can lift it up, you can see a drill that's about the size that you can see here. This ceramic drill has 2,400 connected cooling channels. Each one of them is approximately 100 microns in diameter. Let's drill further down into 3 levels of innovation of this powderless technology. We're here today to celebrate this technology that leverages actually three different levels of innovation. Each of the levels leads to another set of benefits. It starts with the power of stochastic nanoparticles, and I will soon explain what it means. It continues with the competence of jetting more than one material, more than a single material. We jet, and this is key, we jet the build material for the creation of the part and the support material at the same time, 2 different materials. And the beauty, a picture I took again with my simple cell phone, the beauty of ultra-thin layers. It is a combination of very small parts and the random nature of the particles, random or stochastic. What we mean by random is that the particles, unlike most of the metal AM systems that I'm aware of, the particles can be of a random size and they can be of a random shape. And they're very small. Now, this leads to outstanding part properties. In what? Number one, because of this nature, we can get very high density, close to 100% density, after the part is fully sintered. Number two, isotropic, complete isotropic nature of the part. By isotropic, I mean that if you cut it either on the X, in any plane, in any way, you will get the same microscopic structure, you will get the same mechanical properties. It will be very hard to find differences between the different directions. And finally, if you compare, for example, to process like metal injection molding, some people refer to it as MEM, or a process that was discussed here called binder jetting. This is dramatically lower in shrinkage. So it's in every direction, it's half if we compare to these other processes that you may have heard of. We have half the shrinkage of each direction, or overall 8 times less shrinkage. And again, why can we go stochastic? Why can we go into random size or shape? It is because we don't have a powder bed that limits us. Since we work in a liquid form, we can use any size or shape of particles. And this is what leads, and you can see the picture on the right, to 99.9 and beyond density. But it's more than the perfect density. What you see on the picture on the left is a SEM picture. You can get real natural packing, which ends up with properties of the highest quality. If you look at the right and you see this is a stretched dog bone that was printed on the Carmel additive manufacturing system, you cannot tell, those of you who are familiar with metal, this is a stainless steel 316, you cannot tell that it was made on an additive manufacturing system rather than molten metal. So from the hot flames of the part mechanical properties to the calm experience of the technology user. When it comes to the operations, simplicity is king. As we jet directly 2 different materials simultaneously, the build material and the support material, we get some inherent advantages. Start in the left with auto support planning. There is no support planning. The support is planned by the software itself. There's no need for knowledge. There's no need for training your operator. There's no need for any heat considerations. And as I said, there's no need to actually plan the support structure. The support removal. There is no mechanical intervention here. No mechanical removal of the support is needed, since the support that we use, both in metal and ceramic, we use a different material for the support structure, a complete different material. Since it has a physical different properties, we use a simple water-based solution to get rid of the entire support. And last but not least is the safety. Since we don't deal with powder, we eliminated issues that some of you may have heard of once, about static electricity, about inhaling, and about training of fire prevention. All these potential problems that people that did with metal powders are removed from the equation. Let's zoom in. This is how it looks like in the illustration. At the same time, we have, on the Carmel system, we have 24 heads, half of which are on the left, are used to jet the build material. Each droplet includes thousands of nanoparticles. And the same is true on the right-hand side. I just used a different color, but this is to illustrate the different material, and this is the support droplets. And as I said earlier, the support, both the support and the model or the build material comes in a sealed cartridge that is simply loaded into the system. In a recent study quoted by Olaf Diegel, associate of Waller's Association, 70% of the part cost comes from post-process. If we take each brick in this diagram, and each brick illustrates one stage in the creation of the part, and you compare the nanoparticle jetting technology to traditional AM processes, either DMLS or binder jetting, you can see that we can compress the process and save not only complexity or time, but also money. And as it was said earlier today, complexity doesn't come for free. Thank you. In our process, basically, I don't know if you can see, but there are 5 stages. You need to load the cartridges into the system. You press the build button. You move it to the self-dissolving support, sinter it, and inspect it, and you're ready to go. So I use the fire to illustrate the part mechanical properties, and then the simplicity of the green forest. Let's focus on the last level of innovation, the sharpness of an ice. XJet raises the bar for additive manufacturing parts as they come out of the process. And when it comes to geometry, no compromise is needed. Any geometry. The support structure and the thin layers allow very complex structures, including conformal cooling channels for mold inserts or for the drill that Katie showed you earlier. Fine details. As I mentioned, we can do 0.1 millimeter or 100 micron components, near net shape, very close result in comparison to your original part plane, and smooth surface that saves time and effort in getting to the final result. Any geometry allows us unlimited freedom of design. When the support is made from a different material, there are simple processes that apply because it's so different and take care of the support without manual intervention. So it's based exclusively on the different physical nature of the two materials. The details you can see here, or the details that you can achieve, are a result of very small particles. Just as a comparison, in powder technologies, what's the common size or diameter of a part? Just about right. Typically from 20, and this is a physical limitation to go smaller than that because of various reasons. We are talking about 50, 100, and in the case of ceramic, even 1,000 times smaller diameter. Okay, take it to the power of 3 and calculate how much smaller the particles in comparison to powder-based systems. And so that's one parameter. The other one, if you look on the right-hand side and you see the layers, we use layers, and it depends on the material, but from a couple of microns up to about 10 microns, which is few times thinner than any existing metal additive manufacturing system. We're using a liquid, and this makes all the difference. It makes a difference in the properties, it makes a difference in the simple operations, and it makes a difference in the geometry that you can reach. We hope it redefines both ceramic and metal additive manufacturing, and all levels of innovation are summarized in this short video. This short video I choose, we have a couple. This is a short video of ceramic, but everything that you will see in the next 2 minutes apply the exact same way also to metal additive manufacturing.
Previously on XJet.
XJet nanoparticle jetting. Welcome to a new era in metal additive manufacturing.
Now, it's time to demonstrate how XJet leverages the same nanoparticle jetting, or NPJ technology, for ceramic 3D printing, using our new Carmel line of AM systems. Unlike existing approaches, XJet's NPJ is a highly versatile and scalable inkjet-based technology. NPJ uniquely empowers the manufacturing of high-quality ceramic parts of virtually any design, with superfine details, all in a simple and safe process. So, how does it work? Ceramic materials, packaged within convenient cartridges, are easily and safely loaded by hand into the XJet Carmel AM system. With no need for a powder or liquid vat, the Carmel system uses only the materials required. Suspended within our unique liquid formula, nano-sized particles are jetted from thousands of inkjet nozzles. These nanoparticles, of various sizes and shapes, are randomly distributed to allow for natural packing and high density. Liquid droplets, containing either ceramic model or support materials, are simultaneously deposited onto the build tray in an ultra-fine layer. The ceramic part builds up as the tray descends with each pass of the inkjet print heads. After printing, the support component, made of a soluble material, is easily disintegrated, allowing for fast and clean support removal. The non-UV sensitive materials utilized by NPJ technology enable simple single-step sintering. Our versatile NPJ technology empowers the rapid production of ceramic parts with superfine details, unprecedented safety and simplicity, and unrestricted geometries. XJet nanoparticle jetting technology and the Carmel line of AM systems, redefining ceramic additive manufacturing.
Two years ago, on this exact stage, I was presenting here the birth of a new technology, nanoparticle jetting. We've come a long way in the development and commercialization of the technology and its first product line. I'm very happy today that you are here because it's a great opportunity and a great timing to share with you the plans of XJet for the very near future. First step of going out of the lab is to find those innovative early adopters who share the vision and are as excited as we are with the opportunities nanoparticle jetting represents to their business. The previous presentation by Oerlikon happened to be by the company that was the first one to get our first system out of Israel in Europe, and we have additional users in Switzerland, in Israel, in Eastern Europe, and here in North America. They are getting their printers now and start to move the additive manufacturing into its next level, one of which you can see here in the picture, shaking heads with Avi Cohen that some of you know. And right behind them, the Carmel additive manufacturing system. It's a great honor to mention on this stage for the first time our first installation in the United States in Youngstown, Ohio, and to invite all of you to go into our website and register to XJet first open house in America in Youngstown, Ohio on the evening of May 1st. If you want more details, you are welcome to join me at the end of the presentation. In June, to be able to meet the needs of the market, to scale our business, we took another major step and contracted a leading manufacturing company to assemble our systems with an ability to increase production significantly this coming summer. So that's planned for the middle of June. Another major day is coming soon, and I shall take this opportunity to announce the inauguration of the XJet Additive Manufacturing Center, planned for exactly 90 days from today, with an investment of over $10 million, with more than 20,000 square feet and more than 10 unattended additive manufacturing Carmel systems. So this is planned for the beginning of July. And finally, in August, we are moving into our new offices. You can see them maybe. Those of you are familiar, you can see the building behind the team. The building is completed. It will take a few more months to finalize the move. The team is part of mainly the R&D team. And this is really the power behind our powderless technology. And I advise, if you can take one memory from this presentation, I suggest to remember the real power of powderless. Before this presentation comes to an end, I would like also to invite you in a couple of weeks to Fort Worth, Texas, for Rapid and TCT trade show. You will be able to see not only the Carmel machine in action, but most of the leading team of XJet will be there, and you are more than welcome to come and join us.